The purpose of today's lesson is to determine if two figures are similar to each other. Now, if you might recall, over the last couple of days, we were dealing with congruent figures. And as we've said, congruent figures mean they're the exact same shape and size. You can literally lay one figure on top of the other and everything matches up in terms of the vertices, the angles, and the sides. Now we're going to deal with the concept of similar figures. Also, when we were dealing with congruent figures, we dealt with three types of transformations: a translation, a reflection, and a rotation. And one of them was purposely left out because it doesn't fit. And that's what we're going to talk about today. So, first thing is, similar figures. Two figures are similar if they have the same shape, but not the same size. Now, if that is the case, the image can be obtained by a sequence of transformations whether that be a translation, a reflection, or a rotation, and a dilation. Finally, corresponding angles are congruent. And just to add a little something to that final statement, as we've discussed in class, all triangles which have three angles, those three angles add up to 180 degrees, no matter how large or how small the triangle may be. So therefore, if I take the world's smallest triangle and the world's largest triangle, they still will have angles that measure 180 degrees in total. Scale factor, you're familiar with this from dilations, but the technical definition is it's the ratio of a side length of the image, so the after, to the side length of the original. And then finally, if I match up the corresponding sides of two similar figures, the ratio of those lengths of the corresponding sides are equal. And what we're just simply saying there is, if the two figures are similar, they have the same scale factor, and so that scale factor is the same throughout the entire figure. Okay, now what we want to do is the following. We want to take, and I'll write the coordinates of the figure off to the side here. Let me just align this up. And you will graph, if you haven't already, the figure. And you're going to tell me if they are similar. So we're going to take triangle ABC. A is the coordinate 1, 1. B is the coordinate 1, 5. And C is the coordinate 4, 1. That's 6. So 1, 1, 1, 5, 4, 1 is, we'll start as that is the original. A, B, and C. DEF is comprised of the coordinates 6, negative 1, 6, 7, and 12, negative 1. So 6, negative 1, 6, 7, and 12, negative 1. Now, by looking at it on the face of it, it seems like these two triangles are similar, but we need to be able to mathematically prove that that is the case. Now, how would we do that? Well, we need lengths of sides. Well, you can see by just counting that the length of AB is 4 units, of AC is 3 units, AED is 8 units, and DF is 6 units. And something we will cover later in the course, but we could figure out the length of this diagonal to be 10 under a theorem that you're going to learn, and this one to be 5. So now the question is, are these two triangles similar? And hopefully you'll be able to see that when I compare my longest side to my longest side, my shortest side to my shortest side, and then the remaining sides, I get equivalent fractions, which tell me there's been a scale factor of 2 if I went from smaller to larger. Now, would it matter if I flipped each of these 3 fractions? No, then it would be a scale factor of a half going the other way. Now, just to complete this, if I were to dilate the original figure in black by a scale factor of 2, I would end up with these 3 coordinates. And it would lie here. Well, the problem is, and I'll call that the A prime, B prime, C prime, the green triangle did not end up where the blue is, although they are congruent to each other. So what is the extra step taken to get from the green and the blue? Well, we did 2 things. We dilated the original figure, and then translated it one, two, three, 4 units to the right and 3 units down. So by being able to use a series of transformations, a dilation followed by a translation, I can now make the statement that the 2 figures are similar to each other. Okay, let's go to the next example. No, we don't want to be there. We want to be there. Okay. Now, I'm going to again give you the coordinates for the 2 figures. So the first one is going to be T, U, V, W. T is the coordinate 1, 2. U is the coordinate 1, negative 1. V is the coordinate 6, negative 1. And W is the coordinate 6, 2. So we're going to plot those 4 points. Hopefully you see that this forms a rectangle because I have 4 intersecting vertical and horizontal lines. And then W is the same 6, 2. X is 10, 2. Y is 10, 9. And Z is 6, 9. So I'm going to plot those additional 3 points. And I have W, X, Y, and Z. So now the question is, are these 2 figures similar? Well, as we did before, we need to figure out side lengths. We see that these 2 sides measure 3. These 2 sides measure 5. While these sides measure 5, and the other 2, 7. So we want to create a proportion. Larger side to larger side, 5 to 7. Is that equal to 3 to 5? Well, how do you determine if a proportion is in fact correct here? you simply cross multiply. You get 21, which does not equal 25. So no, they are not similar. Okay? Continuing in that vein, if we take a look at these two triangles, I want to determine if they are similar. Well, I'm going to match up large to large, small to small, and then the next one, odd man out. Are these three ratios equal to each other? Yes. So they are similar. Now, in the next one, you're helped by the fact that there's a color coding of these two figures. But if you didn't have color coding, it's really not that big of a deal. I take the largest to the largest, and I'm going to take the smallest to the smallest. And I just have to test these two out. I cross multiply, I get an untrue statement, so they are not similar. If I fail one proportion, it's not similar. I have to pass all three to, in fact, be similar. So, to recap today's lesson, what we did is we determined if two figures are, in fact, similar to each other by coming up with the ratio of the corresponding sides of the figures. And if each of those ratios are equivalent to each other, then the two figures are similar.